So we're going to look at how limits and continuity work together. Now, you may have an idea what a continuous function is or a discontinuous function is already. But we're going to formalize it a little bit more in terms of continuity at a point and discontinuity at a point. So, most of you are aware that if you can draw a function that is continuous, as in we don't pick up our pen, it's continuous. We can see the continuity. Now, again, for discontinuous functions, we've probably seen a couple where you come to a point and then we jump down here and we can move on. Now, in these cases, we're going to be looking at continuity at a particular point C. So, we are going to define this to be, it has to be defined on an open interval for your function. So your interval, I could go from A to B on both of these functions. For some interval, I'm looking from A to B. It's going to be continuous if that x value, first of all, is defined in that open interval. So between A and B, I've got a value C that is defined between A and B on my x-axis. Same thing here, between A and B, I've got some value C that's contained. It's going to be continuous if and only if you, or I guess if you have, for your limit of your function as you are approaching C, so let's look at this one here that is continuous. As we approach from the left-hand side, as we approach from the right-hand side, the limit value is equal to your f of C. And in this particular case, my value f of C is here, which is also what my limit is going to be for this graph. Whereas here, as I approach C from the left-hand side and the right-hand side, I don't actually have a limit, first of all, but I do have a value for f of C. So this one here, the limit does not equal your value at f of C because it's got a break in there. Hence why it's discontinuous. So, like it says here, if the limit does not exist, or if it does exist but it's not equal to f of C, we say that it's got discontinuity or it's discontinuous at x equals to C. So the key thing with this is that we're not looking at the graph as a whole, we're looking at it at a particular point C for all of these graphs, all the functions. Now there are different types of discontinuity that we need to talk about, and some of the things that we need to focus on are related to how this discontinuity is different between different types of graphs. Now the things that you have to keep in mind is there's basically three things that you have to have in order for it to be continuous. There has to be an f of C that's defined. There has to be a point there. There also has to be a limit that exists for the function as you approach C, and then those two things have to be equal. So let's look at removable discontinuity first. There's also jump discontinuity and infinite discontinuity. For removable discontinuity, this is something you may have seen something similar. It looks like it's pretty continuous except for maybe at C there is a external point. So in this particular case, we have a limit as we go from the left-hand side and the right-hand side. Our limit value is here. We have a value for f of C up here, but the limit does not equal your f of C, so it fails the third condition. Now for removable discontinuity, the reason they call it removable is if we were to remove this point from the function and redefine it to be the limit, it would be continuous. So if we could change one point and only one point, we could theoretically make this a continuous graph. Now for jump discontinuity, again you've probably seen these a few years ago for the types of graphs, but if you had something that basically jumps between where it's approaching to and where it jumps to, again we do have an f of C value because in this particular case it's filled in. We do have a value there at f of C. But the limit as we go from the left-hand side and the right-hand side, the two one-sided limits do not equal the actual limit. So, or they're not equivalent, so therefore there is no actual limit. So because there is no limit, this is discontinuous as well. Now for jump discontinuity, you may also see something like this where you have an open circle and a solid point up here, which means my f of C is actually up here. that is also another possibility as well. So your left-hand side, right-hand side, they don't equal, and you do have a point, f of c, that's above and not part of what look like the continuous aspects. You could also have it like this, where you don't actually have a value of f of c, where you have two open circles. All of those kind of fall into jump discontinuity. Now, there is one thing that we would also need to focus on with these sort of scenarios with jump discontinuity, but I'll talk about that in just one second. Now, for infinite discontinuity, this one sounds pretty much, well, looks how it sounds. You have asymptotes. So, once you have an asymptote, we know it's not going to be continuous because there is that point that cannot exist. So if I had something that went like this and went up to infinity and came down like this, theoretically the limit exists because the left-hand side and the right-hand side are both approaching infinity. And there is no actual value at that point, but we could say it's undefined, right? So in this particular case, it's discontinuous at this value c, and it's infinite because it looks like the limit's approaching infinity. Again, it's not an actual value, it is a theoretical value. Now, one thing about infinite discontinuity is it's not just if the limit is going up to there, it's also if you have, let's just say I have an asymptote and one side of it goes to, and let's just say it stops right here. It's still discontinuous. Your f of c exists here at this particular point on the asymptote, but this graph is going to infinity, so it's never ever going to join up. So again, it's still discontinuous. If you also had two-sided asymptotes, one going up, one going down, still discontinuous. So it's never ever going to join up. That point is always going to have a jump, a discontinuous aspect to it, but we refer to it as infinite as soon as one side goes up to infinity. Now going back to jump discontinuity, there is something referred to as one-sided continuity. There's left-sided continuous and right-sided continuous. So you may see this in the homework if it asks you if it's right-sided continuous, left-sided continuous, is the whole thing continuous. And again, it's looking at the limit from the left-hand side and the right-hand side if it's equivalent to the point. So in this particular case, let's make one of these have an actual point. If I looked at this graph up here for my jump discontinuity, I can say it is right side continuous because the limit of your function as you approach from the right-hand side is equivalent to my f of c value. This one here, I cannot say that it's left side continuous because the left side is not equivalent to that value at that point. It does have a left side limit, but it does not have a value at that particular point. Now, similar to the limit laws, we also have some basic laws for continuity. If f of x and g of x are both continuous at c, then all these laws are also basically true. Addition of two functions is also continuous. Subtraction of two functions is also continuous. The product of the two is continuous. A constant times one of them is also continuous. And the last one, division, again, as long as the denominator, when you plug in c, is not equal to 0. Now, one thing that's a little bit different that we haven't talked a whole lot about is composition of functions. For a composition of functions, if your g of x, which is what's being plugged into a composition function, is continuous at x equals to c, and the f of x is continuous not at c, but of g of c because that's what's being plugged in, then the composite function is also continuous at x equals to c. So just keep in mind what's being plugged in is going to be x is equal to c. Therefore, your outside function has to be continuous at g of c for the whole thing to be continuous at x equals to c. Now, a little side note, when you're working through your homework, I think I did include just the odd numbers. Some of them use something that's called the greatest integer function. Don't worry about those ones. We're not going to be tested on those ones, and we're not going to be focusing a whole lot on it. Basically, it's just a step function graph. So you will see that a little bit more in university calculus, but very minimal amounts.